Okay, so now we're going to be looking at another speed control question, but this one is with a shunt motor. Okay, so the question says we have a 40 kilowatt, 500 volt DC shunt motor, and it has an armature resistance of 0.35 ohms, and it draws full load armature current of 100 amps. Calculate the value of the resistance needed in series with the armature circuit to reduce the speed by 20% and decrease the torque by 20%. So we've drawn the circuit here, and you can see I've got the armature resistance, and the field winding, and then this resistor over here in series with the armature. This is the resistor they want to know. So what is that value? So what is that value of that series resistor? And because we are controlling the armature resistance, or we're changing the armature resistance, we should be expecting a decrease in speed. And this is what the question's asking us. And the next important thing we need to know is because it's a shunt motor, we can look at this drawing here now, and we say that the armature is parallel to the field windings. And if this motor has a constant voltage, so 500 volts is across the armature, the same 500 volts is also across the field windings. The field windings hasn't changed in this problem. So it's got the same number of turns and the same resistance. So they haven't told us what the resistance is, and they haven't told us how many windings it is, but it hasn't changed. So because of that, the same current will flow through that circuit, irrespective of the speed. So as long as that voltage is the same and this resistance is the same, the current for the field will be constant. So therefore, we can say that the flux that this field is producing at the first speed at 100 amps will be the same flux that it produces at the reduced speed, at the slower speed, when we put this resistor in. So the two fluxes will be constant. Then, if we look at this formula, the torque formula, so this formula, or I should say this relationship, it comes from this formula on the formula sheet. So this is the torque formula here. All right. And if you look at 0.318, your armature, sorry, your number of conductors, your lap or wave wound, which are your parallel paths, or your pole pairs, those things all stay constant. So what we call those is K. So those are constant, but the two things that aren't constant is the armature current and the flux. So what we can say is that the torque is proportional to the armature current and the flux, because if you change the armature current, the torque will change because these two are multiplied. If you change the flux, the torque will change because the armature current and the flux are multiplied. So we get this relationship. So if we change the armature current, the torque will change. If we change the flux, the torque will change because the armature current and the flux are being multiplied together. All right. So using this relationship, we can say that torque 1 equals flux 1 times armature current 1. So it's that formula there, over T2 equals flux 2 over armature current 2. And just like we said earlier, because the two fluxes are constant at the two different speeds, because it's a parallel circuit and we have 500 volts over here and 500 volts over here, and this resistance is constant, therefore we can cancel out these two fluxes because they will be the same. And then we have a nice easy formula, T1 over T2, armature 1 over armature 2. And then we can calculate the new armature current. And how do we do that? Because what they did in the question here, they said that the current, or sorry, the torque 2, the new torque at the slowest speed, it's 20% reduced. Okay, so what that means is it's 20% less than T1. So another way we can write that is T2 equals 0.8 times T1, or you could say 80% of T1. So that's why we wrote 0.8, because it's 80%, 20% reduced. So then we're going back to this formula, and we can say T1 over 0.8 T1, because we substituted T2 with 0.8 times T1, and then we can cancel out these two T's, and then we can very easily calculate what the armature current 2 is, which is 80 amps. So you can see now, because we've added this resistor in, the current through the armature has decreased. Then what we do is we're going to work out the back EMF of the motor. Now we put the 500 volts, the first current, which is 100 amps, and the resistance of the armature, and we get 465 volts. And now what we do is, and now take note, we're going to look at this back EMF again. What do we expect the back EMF to be when we put that resistor in to slow the motor down? Do we expect the back EMF to be more, or do we expect it to be less? And the answer is we expect it to be less, because the motor is going to be slowing down, and that means that the back EMF is going to be collapsing as the motor slows down, because the back EMF at standstill is 0. Okay, so then we go to this formula from the formula sheet as well, this one here, and we're going to cancel out the K's because it's the same motor again. And what we're going to do is we're going to say E1 over E2, N1 over N2, and we're going to cancel out the two fluxes. So we cancel out the two K's, which were over here, cancel those out, and we also cancel out the two fluxes. Why? Again, because it's a parallel circuit, shunt motor. So we can cancel out those two fluxes. Then we have the back EMF for the first speed. We want the new back EMF at the slower speed, and we have N1, which is well, we don't have N1 actually. So we don't have N1, but we have they told us in the question that the speed is being reduced by 20%. So therefore, N2 equals 80% of N1. So that means it's reduced by 20%. So it's 80% of N1. Then with that, we can substitute it in, just like we did with the torque, and we can cancel out two N1s. So we substitute N2, we substituted 0.8 N1, and then we can cancel out the N1s, and then we only left with E2, and we get the new E2 to be 372 volts, which is less than E1. So as the motor slowed down, when we put that resistor in, the back EMF has also collapsed. It's starting to collapse. It's slowing down. Then we can go to the back EMF formula. We can substitute the new back EMF in. We can substitute the new current in, I armature 2, which we calculated, and we get the total armature resistance, which is, if you just look here, it's that resistor plus that resistance of the armature. So that's the resistance we add, and that's the armature resistance. So how would we get what this resistor is? Very simple. We would just subtract. So I'll show you over here. So the additional resistance is the total armature, which we calculated, the total armature resistance, which is the armature plus the resistor we put in series with it, and we subtract the armature resistance from that, and we get 1,25 ohms. So this resistor that we're going to add is going to be 1,25 ohms. And when we add that resistor, we are going to be slowing down the motor. So I hope that helps, and I'll see you in the next video.